Hey, welcome back everyone to our Calculus 3 class notes. We are now moving into section 14.6 on page 62, and we're still in the chapter on partial derivatives. In this section, we're going to be talking about tangent planes and differentials. Okay, so first of all, tangent planes and normal lines. We just talked about the end of section 14.5 about a smooth curve being parameterized by r of t. So we're going to talk about the same thing, but now we're going to talk about that curve being the level surface. F of x, y, z equals a constant of some differentiable function f. So we saw that the derivative of f of r of t with respect to t is equal to the gradient of f dotted with r prime of t. Okay, and since f is constant along that curve, since it's a level curve, r, the derivative on the left-hand side is 0, which tells us that the gradient vector, grad f, is orthogonal to the curve's velocity vector. So we actually have seen that before. Okay, so this leads to the following then. So definitions: the tangent plane at the point P naught of x naught, y naught, z naught on the level surface f of x, y, z equals c of a differentiable function f is the plane through the point P naught normal to the gradient of f, which is evaluated at P naught. So this is just like an extension of finding the line that is normal to a level curve. So we have now that we have a plane. Okay, so the plane is just f sub x at p naught times x minus x naught plus f sub y at p naught times y minus y naught plus f sub z at p naught times z minus z naught equals 0, right? Because we have that the tangent plane has the normal vector, so the tangent plane to a surface, right, is going to be tangent to a level curve, and we know that the gradient vector is perpendicular to a level curve, so it's got to be perpendicular to the tangent plane. So that's how we can come up with this equation. Now the normal line then would just be the line that goes through the gradient vector. Okay, so the gradient vector is the line that is the vector that we're going to use as the vector parallel to the line. Okay, so that means that x equals x naught plus f sub x at p naught t, and y equals y naught plus f sub y at p naught t, and z equals z naught plus f sub z at p naught t. Okay, so we're just using the gradient vector at that point to be the vector that's parallel to the line. That's called the normal line to a surface. Okay, so it's actually normal to the surface, which is normal to the plane that's tangent to the surface. All right, so find the tangent plane and normal line of the level surface f of x, y, z equals 0, where this guy is f of x, y, z, okay, at the point P naught, which is 1, 2, 4. So the solution is easy. We just take our gradient vector of f, and we find that that's 2x, 2y, 1. Evaluate that at the point 1, 2, 4. It's the vector 2, 4, 1. So the tangent plane, that's my normal component, so 2, 4, and 1. So 2 times x minus x naught, which is x minus 1, plus 4 times y minus y naught, which is y minus 2, plus 1 times z minus z naught, which is z minus 4. Set that equal to 0, and if you want, we can put in the standard form for the equation of a plane, which is ax plus by plus cz equals some constant, and that gets simplified to 2x plus 4y plus z equals 14. Find the normal line then is very simple. It's perpendicular to the tangent plane and thus the level surface. So we use the gradient vector evaluated at 1, 2, 4 as the vector that's parallel to the line. That's 2, 4, 1. So that goes right in here. These are the v1, v2, v3 for the standard equations for a line, parametric equations for a line. This is x naught, y naught, z naught. So we have x equals 1 plus 2t, we have y equals 2 plus 4t, and z equals 4 plus t.